Well, welcome. Thank you very much, everyone, for joining this session. I hope that the material that we have is of use to you. As you know, we are well, Mike and I, and well, also after Mike retired, we've been working on developing several forecasting tools during my appointment at the WPC International desks. And what I wanted to do right now today is to show you guys these 5 forecasting tools that we have developed. Aside from the Gálvez-Davison index, and link them to what's going on with the synoptic situation so you can see a little bit of the application. As you know, we're all busy, especially if you're a forecaster. We usually, you're almost always on a time crunch. So I understand that we have limited time. So we allocated about 50 minutes for the session. That means that given that we have 5 tools to show, we will not be able to show them with a lot of detail. So this is kind of an overview of the tools that we have developed. And then I will work with Erin for developing some more specific sessions in the coming months to devote these sessions specifically to each tool so we can dive more deeply into the tools. So what I'm going to do today is present these different tools that we have developed at the international desks. So you might be familiar with the Gálvez-Davison index. Mike and I developed the Gálvez-Davison index a long time ago. So I'm just going to go briefly over it because we just gave detailed presentation about 3 months ago about it. But after the Gálvez-Davison index was developed and implemented and used by the different people, the thirst for having different tools continued. So we developed different tools, a lot of them thanks to the feedback from you guys, from all the forecasters and meteorologists and aficionados from the Americas, right? So as you know, in international desk, people come and train with us for 4 months. Well, I'm not at the desks anymore, but Mike and I were there for a long time. So people come at the used to come at the desk and train for 4 months, and also. They weren't only receiving training, but they were also providing us with information about forecasting needs, information about things that they knew or they know, right? Because local knowledge is very important, but also information about forecasting needs. So what were problems in their nations that needed to be addressed and were a challenge in terms of forecasting. So considering that information, Mike and I started kind of thinking about ways to fulfill those needs. So we worked on developing several tools. So some of these tools were developed also with collaborators, and I'm going to speak about all these different tools in this session. So one of the tools is this severe weather and hail environments algorithm. We developed this with a colleague from Uruguay. Then we also developed this FRAM and Airmass characterization algorithm. Then the GDI and dynamics, trade wind inversion, and also an algorithm to help with the tracking of waves in the trades, of tropical waves. All right. So as you know, as you might know, the first index that we developed was the Gálvez-Davison index. So the application desired for the GDI is quantitative precipitation forecasting, particularly in the tropics and in the subtropics. So the main aspects described by the GDI is convective instability for tropical and subtropical convection. So if you're familiar with the different tools that are available to kind of diagnose what type of instability you have available for tropical convection, there are not that many that work. So Mike and I were looking at that, and that was a very significant challenge in the early 2010s, right? So from all these tools, the K index is the one that worked the better. I know Kathy and folks from CMH make some studies about the applications of the K index. But other than the K index and also having precipitable water, which is just moisture, it's useful, but it's just moisture, there was not a tool that actually was able to tell you with in a more detailed way where the instability for tropical and subtropical convection was present. So that's why we developed the GDI. And as you know, well, you can see our names in the index. So Mike and I were the ones that developed that. So I'm just covering this very quickly because I'm going to highlight the other tools. So the GDI has a lot of applications. It's particularly good for excessive rainfall forecasting. Gives you an idea of where the environment has the potential for excessive rainfall. Then it's great for planning routes on aviation because it helps you to find where the deep convection might occur. It's also very good for detecting impactful weather systems, particularly if they're associated with deep convection. Tropical cyclone structure analysis, not necessarily the strength of the cyclone or if it's going to intensify or where it's going to go necessarily. That's a different story. But the structure of the cyclone, where the feeder bands are, all these convective structure can be captured by the GDI pretty well. And there's actually an article on this. It's also great for tropical wave tracking, detection of environments for the formation of mesoscale convecting systems, and so on. So this is what the GDI is good for. I'm going to keep going. Now, the GDI is available in many places. It is available on the WPC website, right? Inside the WPC website. So you just go to the WPC International Desk and you can find it. But it has been also coded in different weather services. We got a request from South Korea about 10 years ago, and they coded the GDI in the internal systems. Then the Mexico Weather Service of Mexico also has the GDI coded. Brazil also has it coded internally. El Salvador used to have it coded as well. So Uruguay used to have it at a time. So there are different weather systems, weather services, and other institutions that have the GDI coded. Also, the GDI is available in in private companies, and they also have it coded. And finally, you can find a comment module of the GDI. So all this information is available. I can provide the links later. Also, when we provide all the information from these presentations, the presentation and these links. All right. So the GDI was the first tool that we developed, but then we developed other tools as well. So the next tool that we developed was the severe weather and hail environments algorithm. And we developed this with a colleague from Uruguay, Nestor Santayana, who works in the Weather Service of Uruguay. And the goal of this tool was to help with the detection of severe weather and specifically hail in the Rio de la Plata Basin. So this is as a central part of South America, right? Subtropical or extratropical South America. So they have a lot of large hail problems in the region. So we decided to develop this algorithm. And it works. It works in the region very well. But as you know, the North Hemisphere is a mirror of the South Hemisphere, so it also works in the North Hemisphere. So it does work in parts of the U.S. and also in the Northern Caribbean. So what is the application desired for this algorithm is the forecasting of severe weather, particularly in subtropical and mid-latitudes of South America, with an emphasis on hail. So it's really good for forecasting large hail. Now, what are the main aspects described? The three aspects that this is really good at is describing a general risk for severity, specific risk for hail, and also gives you information about the upper and low level jet dynamics that associate with the severe weather. So you can see these main things and others with the algorithm. The next one that we developed was the GDI and dynamics. So some of you may have seen that we had a version of the GDI called the enhanced GDI on the WPC website. We decided to decommission that version, or at least deprecate it for a while, because we need to do more documentation and research on the eGDI. So what we did on the International Desk website was to switch back to the GDI, but keep the dynamics included. And why do we want this? Why do we want this GDI and dynamics? The reason is that the GDI alone, like any thermodynamic index, only speaks about the environment, but it's not speaking about the different triggers, so how the environment is going to use that instability to produce convection. So we generated an algorithm or a forecasting tool that has the GDI and the dynamics overlaid. I'm going to go into that. All right, I should have placed Mike here because Mike provided a lot of feedback here. But anyway, I could, if Mike allows me, I could say that this was also developed by Mike and I, the GDI and dynamics, right? Then the next one is the trade wind inversion characterization. So this is to kind of understand what is the structure of the trade wind temperature inversion. What I mean by that, the temperature inversion is that increase of temperature with height in the lower troposphere in trade wind regimes, or that stable layer that generally associates with the trade wind regimes and that limits the vertical development of convection. You know, when you go to the Caribbean and you have this fair weather cumulus, usually you have a stable layer above. So understanding the structure of that stable layer helps you to forecast the weather because, for example, if the trade wind inversion weakens or breaks, then you can have larger vertical development of convection. All right, I'm going to keep going. The next one that we developed was the front-end Airmass characterization algorithm. We rename it as FRAM. And I did a lot of work on this in the last month at WPC. And this is basically to help us detect fronts and also shear lines.
Something that I want to point out when you're looking at the GDI, please remember the GDI is not a standalone index. The GDI is just a tool that you need to consider with environmental dynamics. So you cannot just go blindly saying, well, the GDI was 40, so I was expecting thunderstorms and we didn't get thunderstorms. Is the GDI is just telling you a portion about what is the instability of the atmosphere, but you need to consider what are the triggers, what are the other elements. So it doesn't mean that the index is failing, it just means that you haven't considered all the parameters. So always keep that in mind when making a decision.
Yeah, thank you, Mike. Yeah, that's a very important point. And that's why we developed that GDI, what we're calling GDID, the GDI and dynamics. Yep. And we're going to go into that and look at it together with the current situation. Okay, so I'm just going to go into the algorithms. This is the last one that I wanted to show, the tropical wave and tracking characterization algorithm. Actually, we started working with that a while ago with Gabriela Chinchilla from Costa Rica, but then we included a feedback from NHC, Andrew Levine, and thanks to Jay Alamo kind of organized the meeting. And with Jay, Andrew Levine, and Bonnie, and Shamal Clark from the Cayman Islands, we fine-tuned this algorithm to help with the detection of tropical waves. So these are the 5 new I'm going to speak about. And again, this is going to be very superficial because we only have about 40 minutes left. I went back to NOAA for a month during the month of August to wrap up some things. And in a nutshell, this is what I did for the algorithm. I did a lot of work on the algorithm. So I recoded each tool to aid with their replication in other platforms. So now the code for each tool, the programming code is much cleaner, and I can share that as well with you guys after the session. Then I also was able to improve the visualization of the 4 tools and also the calculations. Then I was able to develop the legends, which I'm going to show you. Also optimize the operational flow, and then improve the website and online information for each tool. So we'll share the presentation, but basically, if you're familiar with the access of the tools, this is the website. If you go to WPC, the International Desk website, you will find them. So you can access via this link, which I'm gonna share later with the presentation, or you can also access on the site, desk algorithms. And you will access for, depending on which domain you pick, you can see all the different algorithms available. So in this case, for example, what I'm showing here is the Caribbean and Central America domain, and you can see that you have the GDID, you have the twin, you have the growth. This is the hail and severe weather algorithm. You have the front one and the tropical wave. At the moment, if you go to the WPC website, there are some issues because there was some patching that occurred a few days ago, and they're having technical issues with the algorithm. So I'm going to show you right now. So this is WPC website. So look at this. This is the hail and severe weather algorithm. Some of the colors are off, and in some instances, some of these tools are not updating properly, but I understand that they're working on this issue. So given this situation, I generated a backup for these algorithms on my personal website. This is another way that you can access the tools. Yeah, and I know the folks at the desk are working hard on it. Yeah, there were some technical changes on the operating system and on the Wingrid's version, and so yeah, they're working on that. All right, so let's dive into the forecasting tools. So the first one is the Gálvez-Davison Index and Dynamics. And this is what Mike was speaking about. The Gálvez-Davison Index, like any other stability index, is just, it's not a standalone index, meaning that it only tells you about the environment. So it would tell you, okay, the atmosphere has the potential to produce deep convection, but you don't know if the motions of the air are going to limit that formation of the convection, right? So if you have a high GDI, say you have a value that is around the red, and then you have subsidence, then that GDI won't be able to be utilized by the atmosphere to produce convection. So if you just look at the red GDI and you say, oh, I'm going to forecast a thunderstorm, you might be wrong. Why? Because the environment is there, but if the atmosphere, the dynamics are not favoring the use of that GDI to produce convection, then you're not going to get anything. Right? In other instances, you might have a GDI that is low, say in this value, say 22 to 30 greens and blues. But what happens? The atmosphere has low level convergence, low level moisture convergence, for example. And what will that do? What will that do? That will generate moist ascent and be able for the convection to form and use the GDI. And you may get more precipitation than what you thought you would. So including the dynamics together with the GDI is very, very important. And that's why we developed this algorithm, the Gálvez-Davison Index and Dynamics, the GDID. And this is just the GDI in the background. You can see the color shades of the GDI for this particular situation. And on top, you have, I know there's a lot of information, but you have the low level winds. You can see here on the legend, 1,000 to 850 winds. Then also you have the upper winds. So this is the wind average between 400 and 200 hectopascals. These are these beige or light yellow streamlines. Then you also have the low level moisture convergence and divergence, but this is the moisture flux divergence and the moisture flux convergence. So if you can see here, I'm going to zoom in a little bit. These brown contours are moisture flux divergence in the low troposphere. Mike and I were looking at different layers, and the layer that worked was between 950 and 700 hectopascals. That's in general for the tropical, subtropical region of the Americas. So what does that mean? If you have the brown contours, it means that the flow is actually, the moisture is diverging, or actually moisture is spreading out. This associates with subsidence and a drying of the convection, right? Whereas if you have the green contours, it means that the moisture is piling up and you might generate ascent. So if you have a region where you have a high GDI like here, this is just south of Louisiana and Texas, you have a high GDI, it's kind of orange, yellow to red. Then you also have a green contour. That means that your conditions for that atmosphere to use that high GDI are more favorable. So you have a higher chance for developing convection in that region. On top of that, you have a yellow contour, if you see that. So what is the yellow contour? Is upper wind divergence. So and we use the 400 to 200 layer. So that is telling you that also in that region, you might have diverging flow in the upper troposphere, which favors ascent, right? So another factor that highlights the chance for your atmosphere to use that GDI to produce convection. So if you ask me, just looking at this, I have more confidence that convection is going to form here, where you have all these values intercepted, than here. For example, this would be Tamaulipas in Mexico. So in Tamaulipas in Mexico, you have a relatively high GDI, but then you have the brown contours and you don't have the upper divergence. So in this case, the dynamics are not as favorable. One additional aspect that I wanted to speak about is not only looking at what the algorithm plots, but also analyzing your flow. So if you're a meteorologist, if you're a forecaster, you should understand what are the roles of the upper troughs, the upper ridges, the low-level troughs, the low-level ridges, and all the different weather systems that you have. So in this case, we have an upper trough. If you see this, we do have an upper trough in the North Hemisphere trough. And usually the quadrant that is favorable for convection is the southeast quadrant of the trough. You also need to evaluate the movement of the system. So if I animate this and I see that the trough is moving east, then this will give me more confidence that these areas east of the trough might have enhancement and could use convection. Same here. In this case, this situation is the most ideal in this graphic because we have a lot of contours of low-level moisture convergence and the upper divergence. So in this case, I can see that the potential for strong deep convection is higher here. All right. Then the next algorithm that we developed is the FRAM and Airmass characterization algorithm. And this is an algorithm that helps us to detect fronts. And also some of the work that I did when I was at WPC in August was to improve the visualization and also to try to improve the detection of shear lines. So what does it do? This algorithm aids with the detection of the thermal and moisture aspects of air masses, also finds air mass gradients, and also finds or suggests the position of surface fronts and shear lines. So I'm just going to go here to an example. This is for the South Hemisphere. So this would be the algorithm output for a random day. This is not today. This is a random day. So you will see that you have a shaded field in the background. This is a field that speaks about the characteristics of the air mass in terms of moisture and temperature. Then you have these contours. You have the black contour, then you have a red contour, and then sometimes you will get a third contour, this yellow contour. These speak about where your air mass gradients are. And I'm going to speak up, and you can see here on the right what are the different quantities that the algorithm uses to calculate these contours. Then you have these little boxes, which I added last month in August. And these little boxes speak about the moisture convergence. So in some cases, this will help you not only to gain confidence on the placement of the surface boundary, but it would also help you to find where the shear lines might be. Shear lines usually have very, very little or no variability, no temperature gradient across them. But the moisture convergence and the structure of the low-level flow could tell you that you have a shear line. If you look here on the slide, I can find an example about here. If I follow the low-level flow, I can see there's confluence and the flow is entering here. So in this case, I only have 2 dots of moisture convergence, but I've seen that in some cases, if you have more moisture convergence, you can actually see several dots along the shear line. So there's no significant temperature gradient, but you can see that the moisture convergence could help you to find where the shear line is. All right. And this would be the analysis of the output of the algorithm. So if I'm looking at the gradients, if I'm looking at fronts, the fronts usually go on the warm side of the gradient. So if I'm looking at this gradient in front of South America and the Pacific, I would place the front close to the black line, no, in the warm side of that gradient. So in this case, this would be the position of the systems. What does this algorithm look into? This algorithm looks into different things. So the main 2 things that are plotted are these fields called alpha and beta. Alpha is these air mass characteristic fields. So this is constructed using these variables. It uses thickness in the low troposphere and also dew point temperatures in the low troposphere. So thickness relates to temperature, the temperature of the layer, and the dew point relates to the moisture. Why are we using dew point and not relative humidity? Because relative humidity speaks mostly about the potential for cloud formation and saturation. But if you want to understand the amount of moisture in the air mass that relates to these changes of air mass with fronts, you need to use dew point. So we are using generally dew point between 1000 and 925. But for elevated terrain, we are going a little bit higher up, and we're using this layer between 925 and 700 hectopascals. So why not using just one level? Why not use just 1000? What happens is that in some instances, particularly when you have terrain, when you're over continents, even if you're in a flat region, you can have interference. You can have, let's call it noise, from diurnal features or features induced by the terrain. And that noise or those changes are going to be very prominent in 1000 hectopascals. However, if you use 925, the 925 feels a little bit cleaner, so it will help you to visualize the big picture where the main system is located. So we're using both 1000 and 925 to kind of highlight where the big synoptic systems are located. So this is alpha, and then for beta, beta is just beta are the gradients. So for beta, we use the field alpha that we just calculated. So we grab that color field and calculate the gradients of that field. But we also look at other variables. We look at thickness gradients of three layers. We're looking at 1000 to 925. We're looking at 1000 to 850 and also 1000 to 700. Why? Because the changes of air mass can be can appear in different layers, not necessarily one. So for example, in the tropics, a lot of times the fronts are very evident in the 1000 to 925 layers, so very shallow. But in some occasions, if you go to the extratropics, the fronts are more prominent in thicker layers. But also there could be some noise coming from the diurnal cycle or convective systems. So including different layers will help you to kind of filter that noise and see where the main gradients are. And the final one that we use is theta E. Theta E and 1000 hectopascals. So theta E will also help us to highlight the gradients. These are the main things that are shown in the graphic, and we also have some complementary fields. So as you can see in the graphic, we have the winds. In this case, this is not today's situation again. Wait, sorry, this is today's situation. So you can see actually the tropical systems here in the low level flow. But you also have the moisture convergence, which I spoke about to help us find shear lines. So there's some complementary fields plotted as well. Okay, I'm going to keep going. Is there any questions on this? I know there's a lot of information being thrown at you.
There is a question on the GDI. Does the GDI take into consideration high concentrations of Saharan dust when they exist, or is that something that also needs to be factored in additionally?
Thanks for the question. Yeah, the answer is no. It doesn't take into account Saharan dust. It's just the GDI is just using temperatures and mixing ratios in 4 layers of the atmosphere. So, however, even though it doesn't use information from dust, it can help you infer where you might be able to have dust intrusions qualitatively, because dust intrusions are usually associated with, I'm speaking about the Caribbean. Dust intrusions are usually associated with a strong surface inversion and also a very dry air in the mid-troposphere, so very low GDI. So indirectly, you can qualitatively infer where you might have a dust intrusion, but it doesn't use dust for the calculation. Okay. Have you thought to include a line that represents GDI to front algorithm? I've noticed the GDI also helps to highlight fronts and lines. Yeah, thanks for your question, David. I haven't thought about that, but I'll write it down because any feedback is good. the thing is that it's always a challenge to balance the amount of information that you want to have in a plot, right? Because a lot additional information is good, but the plots already have too much. So finding that balance it can be tricky. I actually I had added a couple of more lines into the plot, but I had to remove them because I thought the plots were too cluttered. All right, so for the sake of time, let's move into the severe weather and hail environments algorithm. And we developed this algorithm with Nestor Santayana from Uruguay because this algorithm, because Central South America has a lot of severe weather issues and particularly large hail. So and this is what I'm showing right now to start. It's just an example of the tool and that it works in other parts of the world. Actually, I know that Claudio Amparo is here in the presentation, and Claudio is a great collaborator with verification in the Dominican Republic. He's always sending us verification of different events, and also uses the algorithm. And this is an example of the tool output. So you can see that you have these red and pink contours of the Dominican Republic, and a little pink box, and also in the 00 run you also have kind of the same thing. So you have the same signal that is repeating. So if you see that, the forecaster would see, oh, I need to consider the potential for severe weather. I do need to analyze other factors, right? So I need to see what time of the year I'm on, knowing if this happens here. Well, it does happen in the Dominican Republic, so if you see it there, it gives you confidence that it could happen. And then you will correct your forecast, including risk for severity, right? And then in this particular location, this is what they did, and then this is the verification. So the algorithm showed that, and then they were able to receive hail in these two locations, severe weather and hail. And you can see that there were some trees, some limbs down, blocking the roads, heavy rainfall, and hail. There's a lot of information here, so don't get dizzy. I don't expect everyone to understand this quickly. So this algorithm is kind of complex. What it does, it first calculates a potential for deep convection looking at 5 parameters. After that, once it identifies areas where you have that potential for deep convection, it analyzes different parameters that associate with severity, right? And after that, it analyzes inside these areas as well of deep convection, it analyzes the potential for hail. So if you see this output in the algorithm, you would see that you have these color shades in the background. And this is for South America, this is for Argentina. You see, you have these color shades in the background saying that you have a potential for strong convection, but once you get into the greens and the reds, there's a potential for severity. This is a qualitative assessment. And then in the middle of these regions, you see that now there are boxes, right? Green boxes. But here you have a region with red boxes, and also you have a red contour. So if you have these red or fuchsia boxes or magenta, and you have a color contour around them overlaid over a region of severe weather, then that means that the atmospheric conditions are really favorable for severe weather in that particular location. So in this case, if I were looking at this and gaining confidence that that distribution will happen, then I would forecast severe weather and actually hail for this particular location. Other things that we look into the algorithm are, if you see there's other things that are plotted, I'm going to go back to, where do I have here? If you see there are other things that are plotted, I'm not going to go into detail over these, but we have other variables that associate with severe weather. So we also place them in the algorithm so the forecaster can understand all the other aspects of the synoptic situation that could favor severe weather and gain confidence in what they're forecasting. To finish with this, this is an example of a severe weather situation that happened in the plains of the United States. And one positive aspect of this is that the algorithm actually works. When you have these severe weather events in the southern United States, the algorithm works very well. So it does capture these severe weather events in the southern US. And generally, aligns with what the Storm Prediction Center has to say. So that's good news in terms of how the algorithm works. And I see that a comment from Kathy. Are these boxes advection for moisture? And I think that relates. Kathy, could you help me with the context of when you place your comment on the chat?
Yeah, the front algorithm. Sorry about that. I had to step away for a minute. Thank you.
No worries, no worries. Great. No, they're not moisture. They're moisture flux convergence, Kathy. The same that we have in a couple of other algorithms. Yeah, these boxes are moisture flux convergence. Yeah, that's what they are. Okay, now another algorithm, and we have two more. I'm running out of time. I still have 6 minutes. So this is the trade wind inversion characterization algorithm. Some of you might know this algorithm, and what this does, it helps you to find where the base where the base of the trade wind temperature inversion is, or where the lowest stable layer is present, and also helps you. We added a couple of fields to understand where you might have higher chance of dry air entrainment into your marine layer, and also where the mid-level ridges and troughs are, which speak about the mid-level support. This is an example of the different things that the algorithm measures. So for the colors, these are the background colors. You can see that you have from browns to purples and then basically a dark color. So this speaks about the height of the lowest stable layer. So in this case, browns associate with a lower height, a stable layer that is close to the ground. And then whenever you have blues, it means that your stable layer is aloft, higher up in the atmosphere. And that means that if you get development of convection, your convection is going to grow deeper if you have greens and blues versus if you have browns. If you have browns, the convection might grow, the clouds might be just would have really shallow development and not grow very far up into the troposphere. So this is kind of what the algorithm speaks about. But also we have boxes, and the boxes speak about the strength of the inversion, right? So because it's the strength of the stable layer, it's very important also to understand how strong is your stability. If you have a very strong stability, that means that your crowds are going to grow until that stable layer and not be able to keep growing. They're going to spread out. But if you have a weak stable layer, part of that ascent could continue and you will reach higher layers. Maybe you're not going to get a very quick formation of a cumulonimbus, but you might still get a little bit of development across that stable layer. And that is important to know. Why? Because if you have convection that is growing and is penetrating your inversion, your stable, let's call it stable layer, it's going to penetrate your stable layer and continue growing, it's going to start interacting with that air mass that you have above it. And if you have a very dry air mass above that stable layer, what that's going to do is going to bring that dry air into the marine layer and generate drier conditions. Basically, lower your relative humidity and lower your chances for convection to form. You're gonna simulate these dry air entrainment processes. That's why it's also important not only to know how low your inversion is, but also how strong it is, your stable layer. All right. So to finish with this, and I'm already running out of time. To finish with this, as you can see, we are looking into the layers between 1,000 and 650, right? We're looking into these layers, and we're looking every 50 hectopascals going up, right? So what we're doing is we're looking at we're comparing the lapse rate or the change of temperature with height with these ideal lapse rates. Like we're using 2.5 degrees per 50 hectopascals for the lowest two layers, and then we're using 3 degrees per 50 hectopascals. So what happens, for example, if the algorithm finds that the stable layer is this one, the first stable layer, first it looks at this, then at that, and then once it reaches this layer, it finds, oh, the atmospheric lapse rate is actually the warming of temperature with height in this layer is larger than 3 degrees Celsius. Oh, so this is a stable layer. and then this uses different thresholds to determine whether your stability is weak or is strong. So this is how we can calculate the stability, where the stable layer is and the strength of the stable layer. Any questions so far?
Let's see, there is one. I know the information on the WPC site is based on GFS data, which means the accuracy of the information is based on how well the GFS is performing. Are you aware of cases where GDI and the other products are coded in WRF model?
Yes, that's a very good comment, and indeed, yes, this is biased to whatever model is used for its calculation, right? I am aware of a GDI that is coded in other models. Yes, I don't know if about the WRF. I think some people have done that, but I'm not aware where you can find information of GDI coded in the WRF model. Some private companies that have coded the GDI in other models, whether that US is one. You're totally right, and that's something that I want to get into. I would like to get into coding these tools in different models as well, because as you said, this is biased to the GFS solution, and if the GFS is wrong, that means the algorithms are going to be wrong as well. So yes, that's a very good point. Yeah. Thanks, Abby. You're right. First, I'm going to address David's comment. You're right. When you use higher resolution models, then a lot of the tools become noisier. The GDI does become a little bit noisier, and the models start resolving. The models start resolving these like small scale features that some of them are actually spurious, right? I mean, they could see, for example, a potential for convection, but once you go into higher resolutions, the convection could be in a location that is not exactly where it is in reality. So actually, you could get these noisier fields, and the algorithms will also respond to that. Your GDI field is going to become noisier, but that becomes worse with other algorithms. That use, for example, algorithms that use small differentials, calculation, for example, of vorticity or divergence, that becomes even worse. So yes, resolution is very important. And you can also see that what David mentioned with the 0.25 GFS, for example. If you look at the 0.25 GFS versus the 0.5 GFS, you could also see that problem. Yeah. And to address the other question about why 3 degrees, well, this is basically looking at climatological lapse rates in the Caribbean regions of subtropical America for these layers. So looking at climatological lapse rates and also looking at algorithm output versus satellite imagery. And what I noticed is that this was a very decent threshold for the algorithm to capture where the stable layer was. It not only aligned with the described climatological lapse rates for those layers in the Caribbean, but also by looking at satellite imagery, this was a good approach. I remember that I tried using 3.5 degrees as the base lapse rates for these layers, and it didn't work very well. And when I used 2.5 degrees, like in the lower troposphere, it also didn't work. When I used 3 degrees, the algorithm was able to capture better this where the stable layers were when looking at convection development and also soundings. So, and there's room for improvement, I'm sure, but this is the reason why we use 3 degrees. This is the last one that I wanted to show, the tropical wave tracking algorithm. And what this uses, this is just an overlay of 5 different parameters. It's not an algorithm. It's not like a cooking recipe, right? That you put a pinch of this and a little bit of that, like the GDI, for example. The GDI is kind of a cooking recipe. You calculate different things. This is just an overlay of parameters. And as I mentioned before, we developed this in combination with with colleagues from the Costa Rica Weather Service, Gaby Chinchilla, the international desks, and also including the National Hurricane Center folks for feedback. And these are the 5 parameters that are plotted in this algorithm. First, we have cyclonic curvature relative vorticity in the shades of color. So instead of just grabbing vorticity or cyclonic vorticity, we extracted the curvature component of vorticity because vorticity can have a shear component and a curvature component. We extracted the curvature component, and this is what is plotted. We use this layer, 850 to 600. Why? Because this layer we did a lot of trials at the international desk, and we realized that this layer aligns pretty well with where the vorticity associated with the waves is located. Then we also overlaid the winds of 700 and 850 averaged, which also, it's a layer where you can generally see the rotation associated with the waves pretty well. Then we added this. This was thanks to NHC as well. Number 1 and number 3 are thanks to the feedback from NHC. We added asymptotic potential vorticity in this layer, the 320 to 325 Kelvin layer. I'm not going to go into details on this, but basically this helps us to track the waves because it's a conservative quantity and it relates to rotation in the mid-troposphere. So we added these yellow contours as well. And then we added the GDI. The GDI kind of helps it to evaluate the convection that could be coming with the wave. And also we added the moisture flux convergence, which are these green boxes. And the moisture flux convergence tells you about the triggers where the moisture could be converging in the low troposphere. And having all these 5 parameters together can give you an idea of the types of waves that you have. So for example, when you have a negatively tilted wave where the moisture convergence is usually ahead of the wave axis, you will be able to see that in this algorithm, right? For example, here, you can see that you have the moisture convergence ahead of the wave axis. So this is a drive wave that might have some vertical development of convection ahead of the axis. It's going to be short-lived and produce very little precipitation. Whereas here, in this close circulation in the Caribbean, or at least close in this level, 850 to 700, you have the moisture convergence with the axis and behind. So this would be a positively tilted tropical wave. So this doesn't only help you to find how the waves move, but it will also help you have an idea of the characteristics of the waves that you are analyzing. It is a lot of info. I know it can be kind of overwhelming, but I promise we'll work on doing more specific sessions where we can look at each tool independently and compare it with the current situation using satellite imagery and other tools. All right. Thank you very much.